Okay, welcome to Maths Linear Algebra. So we are now at this least squares tutorials. So within the next couple of minutes, I would go through maybe 3 or 4 questions. And again, I would put it up onto YouTube once I have edited it. All right, so anytime you have an issue, please stop me. Okay, so we are going to do this question first. We are given the matrix A, which is a 3 by 2 matrix, and we are given B, which is a 3 by 1 vector. And if you remember from your first tutorials, actually you can view each of these rows as an equation, and these are the target of the equation. And the problem is to find AX equals to B. And if we can find X such that AX is equals to B, then we call X the solution if it exists. And it exists only when, so guys, when would it exist? Only it exists when B is in the column space of A. And only when B is in the column space of A, AX, whatever X is, will be equals to the right-hand side. And when B does not belong to the column space of A, then we will never have AX equals to B. Instead, we have AX equals to B hat, some best approximation of B. And here, the word best approximation, we want to find as close as possible. And here, the word as close as possible basically means some distance. And the distance we are typically measuring is the Euclidean distance. So we have reached here, and therefore now we can say, let's find the least square solution if the solution, the real solution, does not exist. So if this does not exist, if this exists, let's find the real solution. If this does not exist, let's find the least square solution. So let's have the picture. Please go to your slides, 7.1.3. And this is the picture that we are always working on. This is B, the solution that we are interested in. It is a point in a vector space. And this is the matrix A given to us. In this case, we are having these values for question 1. And you can imagine that column 1 and column 2 can be combined, linearly combined together to form a subspace. And in this example, it's a subspace of R3. And if B is in the column space of B given to us is 2011, if B is in the column space of A, then B will be somewhere in this blue shaded region. And this blue shaded region is the space of the column space of A. If B is not in the column space of A, then what will happen is it is outside the space. So in this example, it is clearly that B is not in the blue shaded region. And this is the problem given to us. Now, so what are we interested to find? We are interested to find B hat, the closest point to B. And we're interested, and the least square solution is X hat, the parameters associated that we should choose such that we get AX hat to be equals to B hat, which is as close to B as possible. So that's the key idea. Okay. Now, once you figure this out, you realize that we are interested in getting the normal equations, and this was the quiz question. Now let's come back to our tutorial profile. All right, so we are going to find the least square solution, and now I'll work it out. Now in this question, B does not belong to the column space of A. Therefore, actually you can say that the system of linear equation is inconsistent. And now we are going to find using least squares. And to do these squares, we begin with the equation AX equals to B. Actually, to be very pedantic, we shouldn't write AX equals to B. We should write as AX hat equals to B hat. But because most of us are lazy, we just write AX equals to B. All right. Now, we form the normal equation first, because this is what we're trying to find. The normal equation, left multiplied by AT, the A transpose. So ATAX equals to ATB. The problem, of course, is does ATA inverse exist? And if it exists, then we pre-multiply both equations by A transpose A minus 1. This guy, of course, reduces to identity. Therefore, X is equals to this equation, which is our solution for the least squares. So all we need to do now is to plug in the values of A, AT, and we can get this guy and his inverse. So let's work through. And we get, so this is you work out the mechanics by yourself. So I'm just writing down the answers. And B is 2011. We are getting 1911. So we have almost all the whole pieces. We have this piece, ATA. We have ATB. Of course, we need to get the inverse. This is easy because this is a 2 by 2. To get the inverse, 2 by 2 is not difficult, so we'll leave it to you. Now we have the answer. So you work it out, and you have X equals to X1, X2. And now the answer is 1, 2. Okay, so we are done. All right, any questions, guys? So if you look at this is only a page. And this question is the typical questions of finding the least squares. We are given the matrix A, we are given the vector B, and we use the normal equations to solve. And we have this. Okay. All right. Okay, now we're going to do the second question. The second question is a bit more can say easy, which is interesting because you look at this question and you think that it's more difficult because you have a 4 by 2 equation and you have a 4 by 1. So if you proceed on, you can try to do, of course, the whole least squares problem, which is saying that x, because when we say find a least square solution, all we are trying to do is to find x or x hat, and then x hat, as you remember, we just memorize this equation now. And we substitute all this in, and you can figure out the answer. So there's one way that we could have done this. But this question was interesting because this question allows us, tie us to what we understand about orthogonal decomposition. Because it is all about orthogonal decomposition. Where's the orthogonal decomposition part? Look at, again, this slide. The orthogonal part is the error of B being approximated by B hat. This error is orthogonal to the whole plane of the column space of A. Now, if you refer to tutorial 6, you realize that we are always talking about orthogonal projection. Isn't B hat the orthogonal projection of B onto the column space of A? So once we have understood that, then we could use the same principle of orthogonal projection to answer this question. Where is the orthogonal part? Interestingly, if you check column 1 versus column 2, column 1 and column 2 are orthogonal. All right, let's test. Let's call this column 1 A1, column 2 A2, A1 dot A2 is equals to A1 transpose A2. And then if you want to put it, it is 1, 1, 1, 1 multiplied by -6, -2, 1, 7. And now obviously the answer is -6 plus -2 plus 1 plus 7. And it is -8 plus 8, 0. So the first column is orthogonal to the second column. Now, when we are given a matrix that have orthogonal columns, then it is very easy to solve for the least square solution because we could use the theorem that says that, which is theorem 8 at slide 6.2.5, page number 2. Let's go to see it. (6.2.5) here is all about Gram-Schmidt and orthogonal projection again. The problem is this: we are given Y and we are given W, the space that we want to project Y onto. And now, if W is given by an orthogonal basis, means that we are given, let's say, a matrix W, and now we are given U1, U2, up to UP, and they are orthogonal, then, in fact, the answer of Y hat, the projection of Y onto the space, is given by this equation. So this is the exact problem of tutorial 7, question 2. We are given two columns. and these two columns are orthogonal to each other, we're going to project B, okay, onto these two columns. That's the question. So let's come back. And we are going to use exactly this equation. And then you'll realize that the least squares weights are exactly these guys. They are the weights of the x1, x2 to be found. All right, so once you can tie back to this theorem, we can go to our tutorial and solve the questions in that way. So we are going to write AX equals to B, but we are going to say B hat, which is the projection of B onto the column space of A, or sometimes I write it as W, because I'll say W equals to column space of A, is equals to the equation which I have just now said, which is B dot, I'm going to call this U1 and U2. And since there are only two columns, B dot U2, okay. Right. So in fact, we already have a equation to solve for the least squares, different from the normal equations version. But never mind, let's proceed on because we were lucky enough to be given two columns that are orthogonal. So B hat equals to, I'm going to plug in the numbers now. B dot A1. So B, I'm going to write it in full. B dot U1, sorry. B U1 dot U1. U1, so I'll write this in full first for you. -1, 2, 1, 6. U1 is 1, 1, 1, 1, divided by 1, 1, 1, 1, 1, 1, 1, 1, multiplied by 1, 1, 1, 1. So this is, and then plus B dot U2, U2 dot U2, U2. Now, let's try it again, okay, in full. And then we have -6217, and then the rest is -6217 multiplied by -6217. So of course, this is plus. All right, it looks very complicated, but actually, it just simply reduces to 8 divided by 4 multiplied by 1111 plus 45 over 90 minus 6217. So always remember, this is U1, the first column of A. This is U2, the second column of A. Now, once you have reached this point, actually we are done, because it says find the least square solution. What is the least square solution? All right. What is the solution? It's X. Where is the X? This guy is X1. This guy is X2. Why? Because it says B hat is equals to, I'm going to now put these two column vectors as matrix notation, which is 1, 1, 1, 1, minus 6, 2, 1, 7. This is A, of course. And now I'm going to put 8, 4 here and 45, 90 here. So you realize that the first equation, we derive it from theorem 8, orthogonal projection. When we have found the solution in this form, we can cast it into the matrix vector product, AX. Now we see that actually AX equals to B hat. We now can identify X, the least squares solution. Okay. Now, so this is, of course, method one to solve for this problem. If you're not convinced, then we should actually use the least square solutions to solve the exact same problem. So I'll just highlight what we should have done if we didn't use this theorem, because let's say we have forgotten about this theorem, or we have forgotten to check that actually the first column is orthogonal to the second column. So we then go along this question, and then what do we do? Well, we will have just done this. We have just said x. Sorry, we have just done this. Let's start with this. And then we have done and then we just say, found this first, and then we plug in all the values into this equation and we solve. And we would have gotten, okay. But you have done it this way, then you will not have appreciated the fact that the first two columns were orthogonal, and the orthogonal projection was actually a cleaner and faster way to do it. Okay, but you should actually try these two approach. Any questions, guys? Is it possible to make the screen bigger? Oh, okay, sorry. Better now? Yeah, I'll try. There's a problem with my monitor today. Okay. All right. There's no questions. I'm going to try question 3 now. Just shift this out of the way. All right. I don't know why my iPad cannot be sized today. Any questions? No? Okay. Now, I'm done with question 1 and 2. And now let's see question 3. Before we start question 3, I have a question to ask. 1, is the system of linear equation consistent? So by consistent, it always means that I can find AX equals to B. The left-hand side is equals to the right-hand side. This is given. This is given. So always remember, A is given, B is given. Can I find X such that equality happens? If equality happens, the system of linear equation is consistent. If it does not happen, then find the least square solution. So once you look at this equation given to us, the question is, without any calculation whatsoever, can we immediately inform the audience that the equation is inconsistent? And the answer is, in this example, is quite easy, because you look at the first equation. So imagine that we have A, and then we have x1, x2, x3, and x4, 4 variables. So the first equation is x1 plus x2 plus x3 plus x4. That's how we interpreted it, equals to the right-hand side. What about the second equation? Same, x1 plus x2. Oh, okay. I should have written 0 here. And the answer, wow. So in fact, by studying the first two equations alone, we're already done. We can tell the audience that these two equations are inconsistent because actually the left-hand side has the same variable times the constant, and the right-hand side are different. So actually you have two lines that never meets. You'll never find an x that will agree with these two equations even, let alone the other equations. All right, so the least square solutions must be used because there is no x that will satisfy all these, how many? 6 equations. All right, so that's the first thing. We notice that the rows are dependent. See? So the first row and the second rows are the same. The third and the fourth are the same. 5 and 6 rows are the same. So they have dependent rows. They also have dependent columns, which is also interesting. This first column is actually the sum of the second column plus the third column plus the fourth column. Okay, so we now realize that A matrix has dependent column. See, once it has dependent column, we are going to have a problem. So this question is trying to show you that when you have a dependent column, then x equals to ATA minus 1. Let me write the equations down. ATB. This matrix is singular because column of A are dependent. And then we have this fact, therefore ATA inverse does not exist, and we cannot use this equation to solve. We cannot, because we don't have ATA inverse. So this question teaches us another way to solve. Okay, let me see. I have a question here. Can a solution for a consistent be a least squares? Yes, the least squares is because the error is 0. So Chuan Song asks, can a solution for a consistent system be called a least square? Yes, because the error is 0. So error equals to 0, no approximation error, still a least square. The least square meaning basically that there's no other solution that has a smaller error than him. So the word least square, the least square is applying to the magnitude of the error. Okay. All right. What else? Maybe I'm going to try to do it this way and show you what's the problem. Okay. Now, let's do the working first. ATA. What is ATA? Without, I mean, I will just write the answers for you, but you should work it out by yourself. So immediately it is also obvious that the columns 1 is actually equals to column 2 plus 3 plus 4. Can you see? So ATA is obviously has dependent column. When it has dependent column, although this matrix is square, but its column is dependent, therefore ATA minus 1 does not exist. So but you cannot stop here, right? Because it still asks us to find some x. Okay. Now, how would you do it in the real world, guys, if you have achieved your task with this problem? In the real world, typically, we have a few columns, but many rows. And this problem would happen. But let's say this problem happened. Maybe, just maybe, this column is always, in this example, the sum of second, third, fourth column. Now, if you have such a problem, the simplest way to do is to make A2 equals to A1 by throwing away one of the dependent column. So you make the A matrix throwing away dependent columns, you get A matrix that is full rank. Full rank means that I have either full column rank or full row rank. In here, we're talking about full column rank, means all the columns of the new A is independent. Once you have done that, then you realize that if you have done it properly, then you'll become, the ATA will become non-singular. All right, but we unfortunately, it's not us to do this. We must continue and proceed from here. ATA. All right. So in fact, actually, if you remember your tutorial 1 and 2, what we are trying to do is actually this problem. We have ATAX equals to ATB. Now, just imagine that if you have this problem, then, all right, let's calculate what's ATB first. We have 4 minus 4 to 6. That's ATB. We also have this matrix, which is ATA. So I'm going to just write 6, 2, 2, 2, 2, 2, 2. And then you have, of course, x1, x2, and then you have 4 of them because you have 4 columns. And when you recognize it from this angle, then can't you use row reduction? Yeah, which is the Gaussian elimination. And then we are going to do this row reduction. Okay, so what do? We always put ATA and the augmented matrix ATB, and we perform row reduction. So I'm going to write down for you. And then the augmented matrix. And then the rest of them. And then we do row reduction. So when we perform row reduction, then all we are finding is to find the solution of x1 to x4. All right, so you can do it by yourself, but when I perform row reduction, this is my solution. You can check. Now, guys, this is the interesting part. 3 minus 5 minus 2, 0. What do you think the last row of this guy will be if we have dependent columns and meaning dependent row? The answer is we would have a row of all 0, because when we are counting the number of pivots, we only have 3 pivots, showing us that only 3 columns of ATA are independent. So we have 3 variables and one free variable. And then now we can solve. So how do we solve? So remember that, so please refer to your old, what do you call it, tutorials again. Once we reach here, we're going to write the parametric form. And let me use the green again, which is x1 plus x2, 3, 4. x4 equals to 3. So that's the first equation here. All right, so that's the first equation, A. So what about second equation? B. I have, second equation is x2 minus x4 equals to minus 5. And so on and so forth. I'm going to write the rest down. x3 minus x4 equals to minus 2. And the last equation is x4 equals to x4. Once I have it in this form, then I can write the solution, the solution in parametric form with the free variable. So therefore, x is equals to, we get used all these variable, which is 3 minus 5 minus 2. And then remember that is 0 plus x4, so it's 0 here. So this is the particular solution, and this is the free variable x4 running around to give us the, what do you call the infinite solution problem. So we have x4 equals to minus 1 because implying x1 is equals to minus x4. So this is the minus 1 that's running around here. x2 equals to plus x4. x3 is equals to x4 plus x4. x4 is equals to x4. So the answer is minus 1 plus 1 plus 1, and this is of course plus 1. So this is the solution for least squares. So actually this question is not trivial at all. You look at this question, so how did we start? Okay, so I'm going to explain the big process again. We would have thought that the problem is easily solved for least squares because we already know how to write the normal equation. And then from the normal equation, write that x hat equals to that. How to solve the normal equation. We hit a barrier because we found that ATA is singular. And now when ATA is singular, never mind, we cast it into our tutorial 1 and 2 form to use Gaussian elimination to solve for x1 to x4. And that is the trick. Once we have this, then we can still write A. Then of course, then you will say, what is my solution? Actually, the solution can be 3 minus 5 minus 2, 0. Now, if you want to be clever, then you would write it as minus alpha plus alpha plus alpha plus alpha. Then you say alpha is equals to any real number. You realize that AX equals to B hat. This will be the solution that we are looking for. Okay. Anyone? So it's 11:10 now. We have done 3 questions for least squares, showing actually least squares is not just simply, getting the normal equation and solving it. You must study whether there are interesting peculiarities, like in question 3, which is ATA, inverse does not exist, or question 2, which shows that the columns of A are orthogonal, therefore we can use theorem 8 to solve. Okay, so in fact, these three questions are very nice. It gives you a very big picture of what the least squares solution is all about. All right. Any? No? Then I'll just do question 4. But before that, maybe I want to highlight this. Okay. Now, so this is a revision first before we attempt question 4. Again, we have the problem of AX equals to B. This is a very misleading start. If B does not belong to the column space of A, because it's misleading. Okay, let me get someone in, Tian. It's misleading because AX will never be equals to B. What AX can do is to be AX hat equals to B hat. The best X we can find to achieve B hat such that B minus B hat, the norm, which is the length, is as small as possible. And the word as small as possible means least, right? The smallest, the least. The least what? So least square. So you realize that isn't this, let's call this Z, Z equals to B minus B hat. Isn't this Z transpose Z? Isn't this, for example, Z1 square plus Z2 plus, so isn't this? So that's why the word least squares comes in. We want to find the length in terms of the norm, Pythagoras norm, Pythagoras theorem, the norm, the length, to be as small as possible. All right. Okay, so we always come back to this nice picture. All right. So let's erase this first. Now, this is our B, and this is our best solution, AX hat. And we call this B hat. So the hat there says the best approximate of B. Now I could find another X. Let's call it X1, let's call this X2. I could find another X1 and X2. But interestingly, their length, okay, this is their length, will always be smaller than this guy's, will always be larger than this guy's length. So this solution, so this is the least square solution. The least square solution is always smaller than any other solution. So let's call this the solution 1, solution 2 length is smaller than all other solutions. Actually, maybe I should say smaller or equal to, okay? And you realize that in this question 4, then we'll show you that it's actually smaller and equal to. But most of the time it's actually smaller because equal to only occur when the columns of A is dependent. Okay, that's why most of the time we not even considering this problem. But for tutorials and for exams, we have to consider all of these theoretical aspects. Okay. All right. So once we have found this out, then in the lectures, actually I given you a nice example. I have 2 columns. Let's call this U1 and U2. I can multiply U1 by x1 because x1 is a constant, sorry, it's a scalar. This guy is a 3 by 1 vector plus u2 x2. So I'm multiplying, I'm scaling a vector by some constant. I vary the constant. And for each of these constant, I find b hat, because this is b hat, for example. Right? Or let's not call this b hat, and confuse ourselves. Let's just call this sum b. Sum b as I vary x1 and x2. And for every b, I can find an error because I have b minus b. Let's call this, yeah, the approximate. And therefore, when I find the norm, which is the length of the error, where's the length of the error again? Which is always, so if I use some x, so this is b tilde 1. Here, let's call this b tilde 2. How about this guy? This is b minus b2 tilde. This guy, b minus b1 tilde. And I can vary my x everywhere, the whole surface of x, everywhere. And then, of course, I can land myself anywhere in this column space of A. And I can plot the error. So actually, this is the contour plot. And if you have been into the army, the contour plot says that all these lines sharing the same circle have the same height. Now, we are talking about error here. So we want the error to be as small as possible. And then now we plot, and then this is the surface. And this is a convex surface, and there's only one global minimum. And then here it shows us that the least squares, for this equation at least, there is a global minimum. Okay, and this is where we want to find. And this is the problem of all machine learning. You are given A, you're given B, and you're trying to find X to reach the global minimum of this approximation. All right. Now, but question 3 already tells us something, guys. This is question 4, and it tells us, and we think that the answer is a global minimum. But actually, in question 3, shows us that there can be more than one solution. But even though there can be more than one solution, all these infinite solutions achieve the same error. So let me ask you, what is the physical interpretation, the geometric interpretation? If we have actually now, in fact, if I can even do this for you, if I have actually 2 minus 1 and 0. So I have actually column 1 and column 2 to be identical. Then you realize that again, I have one free variable. And if I have one free variable, you also realize that actually it means that I have infinite solution achieving the same error. And if I have that, then can you think how would the surface look like, guys? Anyone? Okay, maybe this is a homework exercise you can go and try, but it will look like something like this. It is a valley. This is a valley. And anywhere you travel along this valley, the solution, the null space, the height of the error is the same. So it doesn't matter. You just go up and down. You're varying this x, but the height the error b minus b tilde doesn't change. So this is one very interesting picture that you can plot for yourself. Now, so let's come back to the question proper. In the question, it says, I'm given A, I'm given B, and I'm given U and V such that AU equals to something, AV equals to something, right? Which is, for example, B being approximated by U, B being approximated by V. So the question is it a least square solution? So maybe you all go and figure it out. You'll be like trying to figure out what is this guy AU, what is this guy AV, and you think that, hey, the smallest one might be the least square solution. But this question is very tricky because, very interestingly, AU equals to 382, okay? And AV equals to 728. Now, if you have figured that out, what is the error? The error is implying B minus BU tilde, the norm. And this is calculated, and I found the answer is square root of 24. What about this guy? B minus BV tilde. Answer is also 24. So in this question, both U and V achieve the same error. So if you actually look at this solution, one way of thinking, why would two different solutions, U and V, achieve the same error? And the answer is this. Look, guys, this point achieve the same error as this point, achieve the same error as all these points. All these points will achieve the same error. Okay? They are the same concentric ring. They are of the same height. They are contours of a convex function. They all achieve the same error. Okay. So if you quickly now answer no, because U and V achieve the same error. And the least square solution is unique. But you have to be very, very careful here. Okay? So the least square solution is unique because we can always find a solution such that it is the smallest. That's the unique part. But in question 3, we have already shown you that it is possible to have infinite solution. So the question is, in this case, was the surface a bowl? That means one global minimum. Or was the surface a V shape such that actually many different solutions get the same error? All right. To answer, please go to section 7.1.3, page number 4, theorem 14. 7.1.3, page number 4, theorem 14. So it says, if A is a rectangle matrix, then everything is equivalent. The columns of A's are linearly independent. And in our question number 4, we check, yes, they are linearly independent. What does it mean? That means all these are equivalent. It means that ATA is invertible, or that we have seen in question number 3 and question number 2. And it has a unique least square solution. Because U and V produces the same error, they are not unique. So this is the real answer for question number 4. We should say in question number 4, because U and V achieve the same error, the least square solution is unique because column of A are independent. And then we are correct. Okay, so you have to reach this point, right? Because if you then say columns of A are independent, then my first question to you is, why are the solutions unique? Right. Now, of course, for sanity check, what do I want to do? I want to have X hat, A transpose A, right? I mean, if we want to cheat, right, all we need to do is we are given A, we are given B, we could have plugged in this, and because A has independent column, then this guy inverse exists, and then therefore now when we play, the answer is, and then when we plug in this, what do you think the answer is? And the answer is actually very nice. The answer is exactly B. That means actually B lies on the column space of A. The least square solution transform is also exactly the solution. Okay, and here again it proves that U and V's are lousy examples, lousy solutions, because their errors are bigger than, in this example, is 0. Okay, we could have found an exact solution. And then I think we are done. Okay, so I've just done 4 questions. I will edit them and put it up when either that or I'll re-record this and put it up in a couple of days' time. Okay. Is there any questions now? Do you have before I leave? Right. If not, if you have any problems whatsoever, please send me an email, and then please do lab number 4 very soon, because I guess in about 1 week's time, we'll begin lab number 4 for the first group. How do you determine the 4x4 matrix? I didn't. In question 3, we do not need to find, we do not need to determine we do not need to find the determinant, because we can identify that the columns are dependent. See? Notice that this column is equal to sum of the column 2, 3, 4. Anyone else? Because once we have identified his dependent column for square matrix, we know that he is singular. Okay, nobody? For chapter 8, is 8.2 and 8.3 not important? Oh, we go. Yeah, we'll go to SV. We'll go to eigenvalue first. Don't worry about chapter 2, 8.2 and 8.3. 8.1 is the most important. It will take us a long time to do it. Okay. So just do the tutorial questions. That's enough. I think we have too much materials, so we are going to cut down some of it. All right. Okay. Okay, Ken. Okay, thanks, guys. So I will see you on Thursday. Okay, bye.